Now we're going to talk about distance between two vectors. That's a concept that comes immediately from the idea of norm, which is roughly the length of a vector. Okay, so if I have two vectors, let's suppose these are two vectors or three vectors, right? Then the Euclidean distance between if A and B represent two positions is simply the norm of A minus B. And so some people would write that this way. So dist is the distance function, says the distance between A and B is the norm of A minus B. And the picture might be this. That's the point A, that's the position B. In this case, B minus A is the vector shown by the blue arrow, which in this case is 2, 1, if we believe if the units on that grid are units. And then the distance between A and B would then be B minus A. That's the same, of course, as A minus B. They're the same thing. So that's the distance between two vectors. And it agrees with the ordinary distance, that you learned about in your algebra class. Certainly for dimensions 1, 2, and 3, it's the same. Sometimes people also will look at the RMS deviation between A and B. So that's the it's just the distance divided by square root n. Okay, so you automatically get distance. Now what's new here is though we can now talk about the distance between 100 vectors, namely vectors with dimension 100. That's interesting. You can't visualize that. Now you can pretend to visualize that. You can claim, in front of your friends that you could say, well, I can visualize. There's one vector and there's the other, and the distance between them is 12. I told you, I can see it. But no one can visualize 100 dimensions, so that doesn't really make any sense. Okay. Now we can get to the triangle inequality, and I can explain how it got its name. So here's how it works. Think of three positions, A, B, and C. These are all three vectors. Now the edge lengths, and I've drawn that down here. So here's A, B, and C. Now, what we're going to do is the edge lengths are, well, the edge between A and B has length norm A minus B. The length between B and C is norm B minus C, for example. And the length between, the distance between A and C, the length of this triangle side, is norm A minus C. Okay? And so we're going to apply the triangle inequality. The triangle inequality says that the sum of two vectors. So first of all, I've added B and subtracted B going from this equation to this equation. So nothing's changed. So I have an equal sign here. And now what I'm doing is I'm using the triangle inequality. Triangle inequality says that the norm of a sum is less than or equal to the sum of the norms. So here I have norm of A minus B, norm B minus C. And what it says is, it goes way back, it goes to Euclid, I guess, and basically says the following. It says that the length of any side of a triangle is less than or equal to the sum of the other two lengths. So that's what it says. So that's why this is called the triangle inequality, the original the inequality for norms. Okay. Now, I'm just as a teaser, we're going to talk about some very interesting ideas that even though norm is a very simple concept, you can actually already see that it's going to, there's hints that it could get super duper useful. So we'll talk about the concept of a nearest neighbor. So if you have two feature vectors, for example, then the norm of the difference, which is the distance between them, that's called the feature distance. And so what that says is you could talk about feature, you have the concept of two feature vectors being close or two being very far away. So, if we go back to that very simple example of regression, we had the house area as the first component, and the second was the number of bedrooms. And so two houses that are close would have probably the same number of bedrooms and similar number of thousands of square feet, right? So that would be, in that case, the feature distance would be small. But a one bedroom, 900 square foot house, right, would have a large feature distance to a 6-bedroom, 5,000 square foot house, right? So that's kind of the idea. So we all of a sudden we have the idea of distance. Now, that's not a geometric notion of distance, right? So that's the idea. Okay, so this brings us to this idea of a nearest neighbor. It's something you will hear about in other courses for sure. Maybe we'll say something about it too later, but let's see. So here, if I have a list of vectors, then Zj, one of these vectors is, and I have another vector x, like a query vector, then what it will say is that among this list of vectors, the one that is closest to x, we're going to call the nearest neighbor. Makes perfect sense, right? So here's x in this picture, and here's my z's. You can see the 6 of them. And the distance between x and the z's, I mean, the farthest one maybe is z1, right? So that's the farthest distance. Intermediate, there's various intermediate distances, but it looks like the winner is z3 here. So you would say that z3 in this set tiny baby example here, z3 is the nearest neighbor of x among z1 dot 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 z6. Okay, so and it makes perfect sense. I mean, you're basically saying of this list of vectors, which is x closest to? Okay, so now you might ask, like, who cares? But actually, immediately, this is a powerful concept in sort of very basic machine learning and data analysis. It's already a very powerful concept. I mean, even though it looks very innocent. Let's look at an example, which hopefully will give you a rough idea of some cool stuff here. Okay, so what we're going to do is we're going to look at feature vectors, which are word count histograms. Okay, so what we did is we took some Wikipedia articles here. I guess there's 5 of them. And we have a dictionary of about 4,500 words. That's all, okay? And then what we're going to do is we're going to take, for each of these 5 Wikipedia articles, we take the entire article and we count the number of words in our dictionary that appears in each of those. So I don't know what the first entry in my dictionary is, but I guarantee you that for these, I have 5 vectors corresponding to these Wikipedia pages, right? And the first entry tells you how many times that first dictionary word appeared in those 5 articles. Okay, so that's it. Now, yeah, don't even try to visualize what a vector with 44 or 23 dimensions is, because you can't. You can pretend you can, and you can, in fact, if you like, you can sort of pretend that it looks like that. Okay, but I mean, I guess it does look like that, just in 4,423 dimensions. Okay, so let's take a look at what happens now. We're going to calculate the pairwise distances of all 5 of these Wikipedia pages. Okay, and all we want to do is to see if it makes sense. Okay, well, the first one is the diagonals are easy because Veterans Day has a vector associated with it. So does and if I say what's the distance between a vector and itself, it's 0. It's the norm of 0 minus 0. So it's 0. So the diagonals are all 0, right? Oh, and by the way, it's also this is symmetric in the sense that the distance between Veterans Day and Memorial Day, which is 0.095, is actually the same as the distance between Memorial Day and Veterans Day. So, I mean, of course, right? So, by the way, in some people, when they give a table like this, they just omit the bottom half of the table because you don't need to see it, because it's the same as the top half. Okay? All right. So now let's dive a little bit deeper. And let's ask ourselves some questions like, among these 5 vectors, which 2 are the closest to each other? Okay, so, and if we just scan across all this, it is indeed Veterans Day and Memorial Day. Okay, and then you'd ask, does that make sense? And the answer is, yeah, Veterans Day and Memorial Day are both Wikipedia pages describing holidays, so they are actually related. In fact, they're more closely related than any of the others, right? We can also ask, what would be the second closest pair? And look at that. It would be, in fact, the Academy Awards and the Golden Globe Awards. Oh, by the way, when I say closest, I mean the ones that are not the same, right? That's kind of amazing because it says that just among these 5 things, the 2 that are closest are the 2 pages that describe holidays, right? The next 2 are ones that describe 2 different kinds of entertainment awards, right? So something is happening, and you can kind of imagine why. Like, I don't know, the the word holiday probably appears in Veterans and Memorial or something like that, but not in the super. Well, okay, not in the Golden Globe Awards, something, right? Okay, um, so it's actually kind of interesting. So we could ask all sorts of stuff here, right? We could say what's the farthest distance, and the farthest distance, I guess, is going to be this: the Golden Globe Awards and the and the Super Bowl. Okay, well, yeah, those seem pretty far apart. Um, Let me just say a couple things about this because you can already do some pretty cool stuff. Instead of doing it with five pathetic articles like this, we could do something like this. We could do this for 5,000 articles, and you could have a new article that you've never seen before, and you could ask, what is its nearest neighbor? Uh, Actually, a very common thing to do is give me the three nearest neighbors. Those would be the one that's closest, the second closest, and the third closest. So these are kind of things. Now, what's stunning about this is how something so profoundly stupid has actually, quote, figured out that, for example, Memorial Day and Veterans Day are related. Now, let me remind you how dumb this is. We've taken the Wikipedia page, two Wikipedia pages, and we have simply counted the number of words, okay, in the page. That obviously we have obscured all meaning. They're no longer sentences. They're no longer paragraphs. It just tells you how many times each word occurred. I mean, that's all it is. It's just really pretty simple. It doesn't understand English. It doesn't understand anything at all. It simply counts the words. And when you do that, it's kind of cool that stuff comes up that you recognize, like it figured out that these two things are close, right? So we'll talk. We'll come back to this kind of stuff later in greater detail. But this should just give you a little hint that even though the concepts we're working with are actually really very simple. It's just the distance between two feature vectors. It's already interesting. I give a couple of examples. Someone comes into an ER. I take their feature vector. It's a feature, but let's say it's 100 long with different things and symptoms, attributes of the patient, all sorts of other stuff. Okay, so I take that test they've had, results. So I take that 100 vector, 1,000 vector, doesn't matter. I take 1,000 vector, and I take that and I run it against all the patients we saw in the last 5 years. Okay, that's a whole bunch of, each one has a feature vector. And then I say, give me the 10 nearest neighbors. That means show me the patient from the past, 5 years who had a feature vector closest to my patient, the second closest, and so on. Now, the closest one is interesting. What we can do then is we can actually do, immediately you can think of cool stuff you can do. You could pull up that file and take a look at it and say, oh, not cool. Oh boy, that patient developed sepsis on day 2. That's really bad. So maybe we better put this one on prophylactic antibiotics right now, or something like that, right? So the point is, it's already like pretty cool that you can already see just with the concept of feature vector and distance. You can already see, you should be able to see that there's practical applications like coming up, right? I mean, give you a perfect example. Somebody says, go buy me a bond. I want this bond. It's going to be issued by this issuer and blah, 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 blah. And you're like, there aren't any for sale. And you go, then what this would do would say, I would make a feature vector for bonds. And someone would say, okay, in that case, go get me a similar bond. And sure enough, you will find a similar bond that is for sale and you'll buy it, right? And actually a lot of things work kind of on just stuff like this.